Alright, today we're gonna cover 6.01 to 6.03, all about waves and stuff. Okay, so 6.01, transverse and longitudinal waves. First, what are waves? Waves are mediums to transfer energy. Waves are made by oscillation of the material. Oscillations of the material. Transverse waves. Transverse waves have oscillations perpendicular to the direction of motion. Example of transverse waves are light waves, radio waves, and infrared. So as you can see, it goes up and goes down, goes up and goes down. So up and down, up and down, up and down. But in reality, it's moving to the right. So therefore, up and down and right, that's like perpendicular. You know what perpendicular means? Go take math. Okay. Amplitude, the max height of the wave. The unit is in meters because we're measuring height. The highest point is called a crest and the lowest point is called a throw. Throw? I don't know what it is. Okay. So yeah, the crest is up there. From crest to crest. Actually we'll get that later. No, here A. From the middle line up to the top of the wave. It's not from the bottom of the wave from the throw to the crest. No, that's wrong. Many people make that mistake. But it's from the middle of the wave to the crest, to the top, or from the middle of the wave to the bottom, whichever you like. Period. It is the amount of time a wave takes to complete a full cycle. The unit is of course in seconds. Well, that was pretty weird. It's time period, from one complete wave, and it's not, basically, what else can you say, time period is just from, actually you can measure from crest to crest. If your x-axis is time, then you can measure from crest to crest, and that's how long your period is. And your amplitude, of course. It's measured in seconds. There's it. Frequency. The number of waves pass a point per second. The unit is hertz. The equation for frequency is 1 over period. So 1 over the time taken to make to make one wave. So this is a low frequency, and there's medium frequency, high frequency. So as you can see, as you increase the frequency, there will be more waves in one spot. That's why as they travel forward, they'll hit one point multiple times per second. It'll hit it faster basically. Wavelength. It is the distance from one crest to the next. That's crest, and that's the wavelength. As you can see that different light colors have different wavelengths. So over here it's in nm, which is nanometers, I think. Red has 610 to 760 Newton meters of wavelength. That's really small. And how about we look at violet? 500 to 450 nm. That's even smaller. Okay, let's move on. There's some more wavelengths here. I'm not going to show that because wave equation. V equals to F. I forgot that symbol's called, but just say wavelength. So velocity equals to frequency times wavelength. So velocity is just the speed of the wave, how fast it travels. So frequency times wavelength. Wave effects. Ripple tank. A ripple tank is used to observe wave effects. That's what a ripple tank looks like. There's a light at the top. It's a clear bottom, so the light can shine through and show the shadows of the highest point of the water. That is called the... Hold on, I wrote it down. Where is it? Where is it? The wavefront. Yes. Those lines are called the wavefront. It is the line that joins all the crest in one line. So there's a power supply and it connects up to a vibrator. The power supply, the more energy you supply to the vibrator, the faster it vibrates. And the more waves it will produce, the faster it will produce. So more frequency, the higher amplitude, you can control that with the power supply. So this is used to study wave effects. Reflection of waves on the surface. So as you can see, there's a wave, original wave, it like bumps into this barrier and then it bumps off. But there is something called the law of reflection, and it states that the where the point hits, it will bounce off the same angle. You just gotta find the normal, then after that you find the two angles. The two angles will be the same. The normal here in this case is right here, and then the angle is theta, and the other angle is also theta. So see, it bounces off the same direction. It's always going to be like that. Wave production and ripple tank. Reflection of waves. A straight barrier standing upright in the water causes the incoming waves to be reflected. So as you can see, it's like, that's what a ripple tank does. It makes waves, and then after that it like bounces off this reflector right there, whoosh, and it comes off there. So like, yeah. Refraction. Change in wavelength. Keep in mind that the wavelengths change due to change in depth. The deeper it is, the bigger the wavelength. So as you can see, there's a deep water and a shallow water and deep water again. When it becomes shallow, the wavelengths decrease. Refraction can also be a change in direction, but it's not always a change in direction. It's usually just a change in wavelengths, but people do that mistake all the time. So for example here, a deep water and then suddenly it's shallow water, but if it's at an angle, then it will change into that direction. See, it becomes long wavelength, short wavelength, but it's also going this direction. Just keep in mind that wavelengths affect the speed of the wave, so therefore it'll remember the equation, velocity equals the frequency times wavelength. So the shorter the wavelength, the slower it is. So when you go to shallow water, it will be slow waves. Diffraction. Spreading out of waves after going through a small point. The effect is prominent when the gap is about the same size as the wavelength. So here's what it looks like in real time. Whoa, it's pretty cool. Small gap. As you can see, the gap here, this wavelength, is almost the same as the gap, and that increases the effect. But if it's a large gap, the wavelength is smaller than the gap, and then it will become like this, where it's like not as prominent as this one, not as curvy, a bit less, This one, it's about the same wavelength, so therefore it's like curving really outwards, like blue. Like blue circles. 6.03 sound waves. Longitudinal waves. The oscillations are parallel with the direction of movement. So as you remember, transverse waves, they move up and down, and then they move to the right. But this one, they move left and right, and they move to the right. So that means that it's parallel. The oscillations are parallel with the direction of movement. They move left and right by using these compressions and rarefactions. Compressions are where there's a point in the wave where it gets compressed, and then rarefactions are where in the wave where it gets expanded. So it's like remember, just imagine like air bubble. Not air bubbles, like air particles. And compressions are where it's like tight, and then rarefactions are where it's like expanded. So then of course the air particles will expand to the rarefaction, and then it will increase there, and then it will move on. Basically it'll just like travel through air and stuff. Examples of longitudinal waves are of course sound waves, and I can't think of any other thing, but I'm pretty sure there's some more. Okay, so a wavelength is from one compression to the next compression. The amplitude is that right there, and this is the displacement of air molecules. What's the difference between transverse waves and longitudinal waves? That's a transverse wave, and there's a longitudinal wave. That's how it travels. See that? Compression, and then rarefaction at the front? That's how that travels, and transverse wave just travels in a wave.
So yeah, that's pretty much all that is about waves. Alright, thank you very much. Don't forget to like,